Okay, so this is section 10.4, page 707. These are disjoint and overlapping events. What we're dealing with in this section, guys, is typically OR problems. And we talked about OR versus AND problems before. OR problems involve doing what? We talked about this with counting. Exactly. OR problems involve adding, AND problems involve what? Multiplication, right? So we're talking about adding here. So what we're talking about what is the probability of drawing one card. So here, we're going to draw one card from a deck. So from a standard 52 card deck. We want to know what's the probability of getting a heart or a diamond. So when you have an OR problem like this, what you do is you have to figure out the probabilities of the two different possible outcomes separately, two different possible categories of outcomes, right? You have to look at the probability of getting a heart and the probability of getting a diamond. And what do we do with those two probabilities, just like with the counting with ORs? Add them together. So, the probability of getting a heart, how many hearts are in the deck? What is it? 13 out of how many cards? 52. So the probability of getting a heart, if you just blindly, randomly pick a card out of the deck, is 13 out of 52, which reduces down to what? 1 over what? I would reduce these whenever possible, guys. Okay? Actually, I should make a disclaimer about that. I'll talk about it in a minute. Plus, how many diamonds in the deck? 13 out of 52, which also becomes 1/4. I would reduce these whenever possible, unless these guys are going to, unless reducing them makes different denominators. Because if we're adding and we have different denominators, what are we going to have to do? Yeah, we're going to have to make them into the same denominator again, right? So there, you'd be better off reducing it after you get the answer, if it reduces, right? Add them together first while they still have common denominators, and then do it. Okay, does that make sense? So for example, if we had 13 out of 52 plus 26 out of 52, I don't want to make this 1 over 4 plus 1 over 2 because now I have to get a common denominator, right? I'd be better off making it 39 out of 52 and then reducing it. So I don't have to worry about making common denominators. Does that make sense? So keep that in mind when you do these. It'll save you some work in a step or 2 steps. Okay, so now this is 1/4 plus 1/4, which adds up to what? What is it? Yeah, 2 over 4, which is 1 over 2. Does that make sense that the probability of getting a heart or a diamond is 1/2? Why does that make sense? It's half the deck, right? Half the cards are either hearts or diamonds, right? The other half are clubs or spades. So it makes sense if we stop and think about it, but this is how you calculate it. These are what are called disjoint events. What makes these disjoint is this. We were looking at pulling either hearts or diamonds out of the deck. Are there any cards in a 52-card deck that are hearts and diamonds at the same time? No. Right? Cards only have one suit. They're either hearts or diamonds or spades or clubs. There are no cards that are the ace of diamond hearts. Right? It's either the ace of hearts or the ace of diamonds. Can't be both at the same time. That's what we mean by disjoint. We mean that there are no outcomes that satisfy both categories. Okay? Let me give you an example of what we call overlapping events. What if we were going to draw a card out of a 52-card deck, and we want to know the probability of getting an ace or a heart? So again, this is an or, which is telling us what? Add. So this is the probability of getting an ace. Whoops, sorry about that. Probability of getting an ace plus the probability of getting a heart. How many aces in the deck? They're not 13 aces. 4 out of 52. Right, there's the ace of hearts, the ace of diamonds, the ace of clubs, the ace of spades. Plus, how many hearts in the deck? 13 out of, which gives us 17 out of 52. There's a problem though, guys, and that is that these are overlapping events. These are not disjoint. What makes them overlapping? The ace of hearts. There is one card, the ace of hearts, that got counted as an ace, and then it got counted again as a heart. We counted it as 2 cards, but it's only 1 card. So what we have to do in this situation is we have to subtract away the probability that that card that you drew was the ace of hearts. Because we've counted it once, we've counted it a second time, so we have to subtract one of those away, right? We do want to count it once. We don't want to subtract both away. We just want to subtract the duplicate counting. How many ace of hearts are there in the deck? 1 out of 52. Now this gives us 17 minus 1 is 16 out of 52, which becomes 4 out of 13. So the probability of us getting either an ace or a heart is 4 out of 13, not 17 out of 52. So do you guys understand the difference between disjoint and overlapping? Overlapping means that there's something that's getting counted in both categories. Disjoint means there is nothing that fits into both categories, or all 3 categories, or however many categories you're dealing with. Okay? The formula for disjoint. Sorry, it helps if I spell it right. Is the probability of getting A or B is equal to the probability of A plus the probability of B. Nothing to subtract because there's no overlap. They're completely separate outcomes. For overlapping, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Sorry guys, I need to restart this real quick. Of A and B both happening at the same time. Okay? Questions about that? 2 different formulas, right? Now, that's the way the book presents it. I would rather present it a different way to you. How would you like me to eliminate one of those formulas? You don't need this one. You don't need this title. The probability of finding A or B is always probability of A plus probability of B minus the probability of A and B. Okay? What if we try and apply that to the heart or diamond? Well, the probability of getting a heart was what? That's an ugly looking heart, isn't it? 13 out of 52. Plus the probability of getting a diamond was what? 13 out of 52. But that's what gave us the right answer. So how am I going to have this thing in here? Minus the probability of a heart and a diamond. Well, out of 52 cards in the deck, How many of them are both hearts and diamonds? 0. So if they're disjoint, guys, that extra little term that you subtract just ends up being 0. So you don't really need two separate formulas to confuse you. Does that make sense? You just have to remember to ask yourself, what is the probability of both of those things happening? Am I double counting anything? If you are, you subtract it. If not, you subtract 0. And it doesn't change your answer. Does that make sense to everybody? So does that kind of streamline that a little bit so it's a little less confusing? It's one less thing for you to think about. You do have to remind yourself, and this does remind you, if you memorize this formula, this term reminds you that you have to ask yourself if there's any overlap or not. And if there's not, that just becomes 0. It disappears. It's one formula. All right, questions about that? Okay. What if I asked you, what is the probability of getting a black card or a face card? So that's going to be the probability of a black card plus the probability of a face card minus the probability of what? A black face card. So what's the probability of getting a black card? How many are there in the deck? 26. 13 spades, 13 clubs out of 52. Plus, how many face cards in the deck? What are the face cards? Yeah, jacks, queens, and kings. Aces are not face cards, guys. Jacks, queens, and kings are the only cards that have faces on them. Right? Faces of people. Okay? So how many of them are there altogether? 12, right? There's a jack, queen, king of clubs, jack, king, queen of diamonds, jack, king, queen of spades, jack, king, queen of, what did I leave out? Hearts, thank you. So there's 12 altogether out of 52, minus, out of those 52 cards, was there anything that we counted in both categories? Are there any black face cards? How many? 6. There's jack, king, queen of clubs, jack, king, queen of spades. So we have to subtract 6 out of the 52 because we counted those 6 as if they were 12. So that gives you 26 plus 12 is 38 minus 6 is 32 out of 52. What does that reduce down to? 8/13 is perfect. Everybody see how that works? Okay. So that's the idea of overlapping versus disjoint. Now, the next thing I want to talk to you guys about, and we've actually alluded to it a little bit when we talked about that other problem, the one or more spades. We talked about going around the back way. But we weren't talking about probability. We were just talking about counting there. We need to talk about complements. If you have the probability of an event, so for example, what's the probability of rolling a 4 on one die? 1 out of 6. Okay? The complement of that event the probability of the complement of rolling a 4 is 5 out of 6. It's 1 minus the 1 over 6. Because what do all the probabilities of all the possible events in a situation add up to? 1. 100%, right? It's 1. So if all the possible probabilities add up to 1, then if you have a probability of one particular event, then the probability of everything else is 1 minus that one event that you've now calculated. Does that make sense? Okay? So if you have a 50% chance of flipping a heads, then you also have a 50% chance of flipping a tails, because 100% minus 50% is 50%. So 1 minus 0.5 is 0.5. Okay? So that's the idea. The way we symbolize this is if A is our event, then the probability of the complement of A is equal to 1 minus the probability of A. So this means the complement, the little bar above the A. So when we talk about the complement of rolling a 4, what constitutes the complement of rolling a 4? What are the other possible outcomes? So does it make sense that this comes out to be 5 out of 6? Right? If rolling a 4 has a probability of 1 over 6, then not rolling a 4, rolling some other number, 1, 2, 3, 5, or 6, must have a probability of 5 over 6. So again, we're not talking about complements having to do with counting. It's with probability specifically. It's 1 minus the probability of whatever event you're trying to find the complement of. Okay? This is kind of like that other problem where we said, okay, instead of doing 1 or 2 or 3 or 4 or 5 spades, we could do all the outcomes minus no spades. Same idea. Because the complement of getting 1 or more spades is getting no spades. Same idea, just with probabilities. Questions about that? Okay, there is another scenario now, another type of situation besides just cards that's going to pop up in here that I want to talk about because some of you may not have a lot of experience dealing with it or thinking about it. Although it's not like cards where you guys don't know what the possibilities are, and that is on page 709, where you're rolling 2 dice. You're not rolling 1 twice, you're rolling 2 different dice, and you have a diagram there on page 709. So everybody turn to page 709 or look at somebody else's book who has it open at page 709. What you have there is a diagram of all the different possible combinations that you can get when you roll 2 dice. The key thing to understand here, guys, the way you want to think of it is that you're rolling them at the same time, so we're not really talking about order here, right? So it's not about permutations versus combinations, but we want to think of it as if order matters. So the way they have that diagram drawn is the way you want to think about it. Notice they have a white die and a red die. Everybody see that? So you want to think of the 2 dice as being different colors. So that means that getting a red 1 and getting a white 2 is not the same as getting a red 2 and a white 1. Yes, it's still a 1 and a 2, but you need to think about which die is giving you which number. It makes a difference. Everybody understand that? Because of that, we're getting 2 different possible outcomes. We're getting outcomes for the red die, outcomes for the white die. How many different possible outcomes for the red die? 6. How many possible outcomes for the white die? So how many possible outcomes for the 2 dice together? And that's what's in that diagram is the 36 possible outcomes. Now, I told you guys that I would allow you to have that little diagram of the deck of cards that you could use on the quiz and test if you're not real familiar with cards, if you feel like that will help you. I told you you can't have anything written on it or anything else Xeroxed with it, but you can have that diagram. You can also have the dice diagram if you want, or instead of, or whatever. Those are the 2 things I will let you use. Nothing else can be on there. You may want to copy it onto one side and then copy the other one onto the other side. Okay, or make 2 pictures of them or put them on the same page. I don't care what size you make them. Don't come in with a poster board with it, but within reason. Okay, I will let you have those 2 diagrams to use on quizzes and tests. So if you feel that you need those 2 diagrams to help you do the problems, by all means, Xerox them now so that you have them, so that you don't forget. Questions about that? Okay. So, what happens if we have a situation, for example, like we want the probability, so we roll 2 dice, and we want the probability of getting a 7, a sum of 7. Well, first of all, how many total possible outcomes are there when we roll 2 dice? 36. We just talked about that, right? The question is, how many of those 36 outcomes add up to 7? Well, what's one way we can do it? 1 and 6. What's another way? 6 and 1. Good. What's another way? 3 and 4, or 4 and 3. What else? 2 and 5. 5 and 2. Any others? That's it, right? Okay, since there's only 6, there's no 7 and 0 on there. So there are 6 possible outcomes. Notice, guys, we did this systematically. I ignored you guys that said 2 and 5 before we said 4 and 3, right? You want to count systematically. If flip-flopping the order, right, which one's red, which one's white, if that makes a difference in the outcomes, then you better flip-flop them before you move on to new numbers, or you're going to leave something out. Okay? So 6 over 36 reduces down to what? 1 over 6. So there's a 1 in 6 chance of rolling a 7. What's the probability that the sum is 11? How many out of the 36 add up to 11? 6 and 5, or 5 and 6. Any others? Nope. So it's 2 over 36, which is... Okay? You guys see how it works? Whether or not you do, Vegas does. All the craps odds are based on this situation, guys, where you're throwing 2 dice. You want to understand the odds in Vegas on craps? You need to study this. This is where they come from, and you'll see the advantage that the house has. What about something like the probability of getting an 8? So 2 and 6, 6 and 2, 3 and 5, 5 and 3, 4 and 4. We don't need to flip-flop that one because it's still 4 and 4, right? It's the same outcome. So there's how many altogether? No, there's no 7s on a 6-sided die. I'm not playing craps with you. You cheat. Okay? What this shows you guys, anybody ever play craps before? If you roll an 8, then in order to win, you have to roll another 8 before you roll a 7. Okay? Which one's more likely to happen, that you roll your 8 or that you roll a 7 and lose? It's more likely that you roll a 7, right? It's no accident, guys. Okay? Again, they didn't build Vegas to what it is by offering fair odds on things. There's always a house advantage in every single game you play in Vegas. Guaranteed. The question is how much of an advantage. Some games have more, some games have less. Okay? All right. Questions about that? Okay. So I wanted to talk about that. Now, what about something like this? The probability that the sum is not 6. Well, what you could do is you could go through that diagram and count how many of them have a sum that's not 6. But there's another way of doing this, guys. The probability that the sum is not 6 is equal to 1 minus the probability that it is 6. How many ways can we get 6? 5 and 1, 1 and 5, 2 and 4, 4 and 2, 3 and 3. Altogether, that's how many? 5 out of 36. So 1 minus 5 out of 36 is 36 over 36. When we get a common denominator, minus 5 over 36, that's 31 over 36. Otherwise, you have to go through and count all 31 of those possible combinations, and it's real easy to miss one. So do you see that this is one of those places where going around the other way kind of makes life easier? It's easier to count how many ways you can get a 6 than how many ways you can't. And then you just subtract from 100%, from 1. Does that make sense to everybody?
You know how to count cards?
Didn't you ask me that before?
No, I didn't.
Thought you did.
No, it's just that.
I mean, I understand the process of it. I don't count cards. I don't play blackjack or any of this kind of stuff.
Well, when you're talking about,
I'm a poker player. I'm not a craps player or a blackjack player or anything else.
you reminded me of the teacher from the movie 21.
No, certainly not. Certainly not. I'll take that as a compliment, I guess. I mean, he ended up being a pretty big jerk, but and a slime ball. So I'm not sure if I should thank you or go over and punch you in the nose, but what's that? Oh, okay. All right. Nice save. Yeah, I wish. No, I'm a poker player. I don't play any of the other stuff. All right. So, questions about any of that, guys? So do you see that there's another way to approach these sometimes that may be less counting than the other way? That's what that whole complement thing is for. Okay.